Has everybody had physics 2? Okay, so hopefully this should be a review to you. Let's make sure that we understand the calculus that's involved here, and then to be able to solve such problems. Our goal is to be able to write the equation of motion. That's our goal. Um, Here, this equation of motion, we use undamped motion. That simply means that if there's a spring that we're trying to investigate is motion, or just a mass, a particle mass, as it moves through space, that there's no external object contributing to that particular flow of the mass. So we only consider the velocity of the mass itself. The mass could be a piece of weight, that's held on a spring, which is the very simple classic example, which is modeled to other phenomena that possess the same characteristics: mass, the force due to gravity. We can equate weight with force, and we can examine how that works out. The question also comes up: how do you determine the so-called period or the frequency of that mass as it moves along a certain dimension? So the two things we connect is Hooke's law. It simply says that the force that is exerted from a spring is said to be directly proportional to the distance of the stretch or even the compression. Either one is still consistent. The strength of Hooke's law is contained in that constant K. If you shrink it first, then K seems to expand. If you pull that string, then K seems to be minimized. Anyway, that's a constant that stays throughout, whether the spring is being stretched or if it's being compressed. So the the glory of Hooke's law is found in the constant. The constant stays the same, and that's mysterious even to the mindset of how we think. The constant stays the same. What are the constants in your life? Well, that's a sermon for these two brothers over there. But amen, amen. The force is said to be K times S. We can look at S, this elongation or this stretch, as the distance x, if you will. And so we have some mass on some spring. We want to calculate the distance of the stretch. Here we're concerned about x, that distance of the so-called stretch. We negate K times S to allow for the restoring force, for this force to return back to equilibrium. How do we get that? By negating this particular force. And so you see the negative here. So what is m times the second derivative? That simply comes from Newton's second law. That the force is said to be the mass times the acceleration due to gravity. Well, this acceleration due to gravity gives us acceleration, if you will, the mass times the acceleration. This acceleration is that second derivative. We equate Newton's second law with Hooke's law, and so we simply get m times a is equal to negative kx. Now from there, we're able to determine the equation of motion, and I want to highlight that. I don't think I have it here anywhere. Um, I should note this before I produce the equation, then we'll work some problems. That if the distance here at from rest, if that distance, the initial distance or the initial displacement, is said to be above the line of equilibrium, then we say that here anything that's above the line of equilibrium is said to be negated. For the natural force is said to be downward. So anything that's going opposite of that is just a negative applied to it. Now, why is that? So the negative and the positive can get us back to the equilibrium, right? Even if it's the initial velocity, if the initial velocity is upward, you just negate it. If the initial velocity is downward, then you put a positive sign in front of it. That's all. So anything that's up is negative, anything that's down is positive, since the natural force of gravity is sucking downward, right? And it just depends on how you define it, because in some models it's reverse. It just depends on, in physics and different other places, they may define it differently, and that's fine. We just base our work on those parameters. Don't have much room there. Let's add a page. If we relate Hooke's law and Newton's second law, we have here this F is equal to ma. It's a lazy m, or the mass times the second derivative of x with respect to that time, and F is equal to this negative k times x. I use x to relate the same movement with respect to the second derivative, right? So this implies that we have m times this second derivative is equal to negative kx. If we get everything on the same side, this is m times this second derivative plus k times x is equal to 0. Let's divide through by the m. So this implies that this second derivative plus k over m times x is equal to 0. Now, just for simplicity's sake, let's let omega square equal to k over m. Let omega square equal to k over m. So thus we have this second derivative with respect to time plus omega squared times x, and that's x of t to be precise, is equal to 0. Now we can solve this, because notice what it is. It's a second order linear differential equation with constant coefficients. Omega is just a constant, right? Because the k was a constant, right? The mass is a constant. So if that be the case, then I can solve this based on the method back in section 4.3. So we solve. Here we have x double prime of t plus omega square of x of t is equal to 0. The auxiliary equation is m squared plus omega squared equal to 0. Remember, this is not Cauchy-Euler, so we don't have to use m times m minus 1, that kind of thing. This is going back to a differential equation with constant coefficients. So this implies that m is equal to plus or minus omega I, right? It's imaginary, right? It's imaginary, right? Those roots are imaginary, right? So this implies then that x of t is equal to c sub 1 times cosine omega t plus c sub 2 times sine of omega t. This is the equation for simple harmonic motion. Have you seen that equation before? Okay. Have you proved it before, or was it just given? Just somewhat given. Okay. So now you know where it comes from, right? And it comes from just the second order differential equation, right? So if that be the case, then we can work some problems. Uh, I wanted to note a few things here. We note the period, right, is 2 pi divided by omega. Then the frequency is going to be just 1 over the so-called period, or omega over 2 pi. I think the only other thing that you need here to know is that the weight is calculated as the mass times the force due to gravity. Also, the weight is force. The weight is force. Right? You let Big Mama sit on you, and you realize that that was some pretty tough force too, right? So, so let's look at some problems here and see if we can work about 3 of these problems before you go. Write the equation of motion given the initial conditions. So let's take number 3. So here I can directly go to the auxiliary equation and write m squared plus 25 is equal to 0. This implies that m is equal to plus or minus, that is 5i. So we get the equation x of t is equal to c sub 1 times cosine. Here the omega is 5, so this is 5t plus c sub 2 times sine of 5t. Now they want us to solve based on those initial conditions. So first they give us x of 0. So wherever we have t, we put 0. So this is c sub 1 times cosine of 0 plus c sub 2 times sine of 0. Well, that just gives us here c sub 1, because cosine of 0 is 1. So c sub 1 is equal to negative 2. For the next one, we need to solve this equation for x prime. So let's take the derivative of that equation. So we get negative 5 c sub 1 times sine of 5t, and this is plus 5 times c sub 2 cosine 5t. So now x prime of 0 is equal to negative 5 c sub 1 times sine of 0 plus 5 c sub 2 times cosine of 0. Well, the sine of 0 is 0, but the cosine of 0 is 1, so this is 5 c sub 2 is equal to, here it says is 10, going back to the initial condition. So we get c sub 2 is equal to 2. So c sub 1 is negative 2, c sub 2 is equal to 2. So we conclude that x of t is equal to negative 2, that's c sub 1, times cosine of 5t plus 2, that's c sub 2, times sine of 5t. Is everybody okay with that? Okay. Let's look at this one. The period of free undamped oscillation, that the formula that we gave was for the simple harmonic motion, and it's undamped. So they're not telling us anything that we don't know. So the period of free undamped oscillations of a mass on a spring is pi over 4 second. So it says the period, and so here the period has a formula. I just go ahead and write it. 2 pi over omega. Here they tell us that this is pi over 4 second. Right? It says if the spring constant is 16 pounds per feet, that is that K is 16 pounds per feet. What is the numeric value of the weight? Can we find W? Here I'm saying that W is the capital W is the weight. Well, I think the good thing is when they give us that period, we can go ahead and solve for omega. Um, uh, why is omega important? Because omega squared is equal to K divided by M. I need that mass, right, to be able to get the weight, because the weight is equal to the mass times the acceleration due to gravity. Right? So here we have this 2 pi over omega is equal to pi over 4. Just cross multiply, and we get 8 pi is equal to pi omega. So omega is equal to 8. So this implies that omega squared is equal to 64, but omega squared has the formula. It's K divided by M. They give us K, that's 16, right? So we just plug that in, we solve for the mass, then from there we can get the weight. So here we have 64 is equal to K, which is 16 all over the mass. So this implies that the mass is equal to 16. I'm just breaking it down, and this is 8 times 8, 16 over 64. So that's just 1 over 4 pounds for the mass, right? And so notice here that I told you that that the weight is force, but at any rate, here the weight is equal to the mass times the acceleration due to gravity. And here, since our units are in the English unit, so we use 32 feet per second squared here for the for G. So we get 1 over 4 times 32 feet per second squared there, and that just gives us here 8 pounds. Okay. Now, hopefully, I got 5 minutes for one more problem, and then I think that'll do it for me for today. Any questions there? Yes, sir. Hmm. Yes, 9.8 meters per second squared is metric, right? But its equivalent in the English unit is 32 feet per second squared. Yes, sir. You got it. Let's see. I need to work a problem that involves solving for the equation of motion, because that's the type problem that I have on the test. It'll be one like that number 9 or number 12. You know, here this problem where it says find the equation of motion, that's good. That's important. So let me work this one, and then we'll go home. So it says a mass weighing 24 pounds. So here that's the weight. 24 pounds, attached to the end of a spring, stretches it 4 inches. So here that's the X is equal to 4 inches. I need to convert inches to feet. So let's go ahead and just do that right now. So this is 4 inches times 1 feet over 12 inches. So that's just 1/3 of a foot. Initially, the mass is released from rest from a point 3 inches above the equilibrium position. Let's interpret that here. The mass is released from rest, which implies that the initial velocity is 0. Okay? So here the initial velocity, that's x prime of 0, here is equal to 0. And then it says that its initial distance, that's x of 0, is equal to 3 inches above. Anytime we talk about above, it's going to be negated, right? If it's below the equilibrium position, it's positive. So this is -3 inches. Again, we better convert that to feet as well. So -3 inches times 1 foot over 12 inches is -1/4 feet. So we'll need that later. So now, let's see what it gives us. It gives us the weight. I'm looking for the equation of motion, right? The key to the equation of motion is omega. I need to find omega. Why is that important? Because you recall here that x of t is equal to c sub 1 times cosine of omega t plus c sub 2 times sine of omega t. So basically we need to find omega. Find omega, just plug it into that equation, and we got the equation. But then we have to use those initial conditions. X of 0 is equal to -3 inch, and then x prime of 0 is equal to 0 to actually solve, for that finalized equation. So to solve for omega, wouldn't that be tantamount to solving for omega square? Because omega square is equal to k divided by m, right? So let's see. So we know that omega square is k all over m. Now, notice here that they don't give us k directly. They don't give us m directly. But I can solve for m from the weight, because the weight is said to be the mass times the acceleration due to gravity here. So we take the weight, which is said to be the mass times gravity. But they tell us that this guy is 24 pounds. So this implies that 24 pounds is equal to some mass that we're looking for times the acceleration due to gravity with respect to the English units, because we're talking about pounds and feet, is going to be 32 feet per second squared. Right? This is times. So the mass is going to be 24 all over 32. And so here, this is 3/4 pounds. Right? That's the mass. So I get m for omega squared. Now I need to solve for k. So what's your proposition of how should we get k from here? From the data that's given, how do you think we can solve for k? Well, let me ask you this. Where does k come from? Yes, sir. I mean, you can. I think that'll be a little bit more into it. Yes, sir. Force equal to negative. Yes. Hooke's law, basically. Yep. We use Hooke's law. Yep. So Hooke's law to solve for k. That is, force is equal to k times s. What's the force then? We have x, right? Tells us that attached to the end of a spring stretches at 4 inches. That 4 inches is the same thing as 1/3 feet. So we have x, right? X is 1/3 feet. Solving for k. What's F? The weight, because weight is also force. Right? So here, this is, just put the numbers there. This 24 for the force is equal to that k times, what did I say? X is 1/3. This implies that k is equal to 24 times 3. What is that? 72. Okay. So good. So now I think we have everything we need. So this omega squared is equal to k over m. We get k to be 72, and m is 3 over 4. So that gives us 72 times 4 divided by 3. What is that? Is that 96? So omega is the square root of 96. What is that? 4 times the square root of 6? Help me out. Is that right? I know you all got calculators. And I would never say that I'm anywhere compared to hidden figures. Those ladies who were called human calculators, they were pretty tough, man. Of which some of my teachers back in the 80s were classified as human calculators. Women, African American teachers that I had. I didn't know why they were called that when I was a student, but now I know. Yes, sir. Hmm. Oh, yeah. What, 96? I worked the problem before I came to class. Just tell you the truth, you know. He said, how did I get it so quick? I worked it before I came to class. I mean, I could have said something to impress you, but I'll be lying, you know, man. I get in trouble, right? So, okay, let's move on. I'm 4 minutes past. So, anyway, this is good stuff. So, so x of t, but to tell you the truth, the way I do it is I took the 72. Remember, the 72 came from 24 times 3. So I left 72 as 24 times 3. That threes would cancel. I had left 24 times 4, and just gave me 96. And that's how I did it. And then instead of to take the square root, I got the 24 times 4. I took the 24 and wrote that as 4 times 6. So the square root of 4 times 4 times 6 is 4 times the square root of 6. That's how I do it. Yeah. So yes, you do use the Christmas tree. Just break all the numbers down into their primes and their composite forms, and then just simplify from there. So here, this is c sub 1 times cosine of omega, which is 4 the square root of 6 times t, plus c sub 2 times sine of omega, 4 times the square root of 6 times t. Now those initial conditions we need, x of 0, that initial condition is negative 1 over 4. So we got x of 0 is negative 1 over 4 feet. And then the initial velocity, x prime of 0, I believe that was 0. X prime of 0. So let's take the first one, x of 0. Just plug in for this equation, plug in where we have t, just plug in 0. So we get c sub 1 times cosine of 0 plus c sub 2 times sine of 0. Well, let's see what that is. This is just c sub 1 because cosine of 0 is 1, sine of 0 is 0. This is c sub 1, but here is set to equal to negative 1 over 4. And then for the next one, we need to find the derivative. So this is negative 4 times the square root of 6 times c sub 1, right, times sine 4 times square root of 6 times t plus 4 the square root of 6 c sub 2 times cosine 4 times square root of 6 times t. And then we said that x prime of 0, this is negative 4 times square root of 6 c sub 1 times sine of 0 plus 4 the square root of 6 c sub 2 times cosine of 0. This is equal to 0. But this gives us sine of 0 is 0, cosine of 0 is 1, so this implies that we have 4 the square root of 6 times c sub 2 is equal to 0. Well, that implies that c sub 2 is equal to 0. So all I have was operating is what's being attributed from that c sub 1. So conclusion, x of t is equal to c sub 1, which is negative 1 over 4 times cosine 4 the square root of 6 times t. That's the equation of motion. Okay. And that's all that I require. So the neat thing here is that the book talks about finding the amplitude and all that. No need to do that. All I'm using is period, frequency, and the weight, right? So those are really only 3 things that I'm using in addition to the equation of motion. So I think you all should be good to go for Wednesday for this test. I think it should be very straightforward. If you have any questions, please just you can come by and see me or email me. But this is basically the test. I'm going to just take those problems, change the numbers, somewhat, and so if you can work these problems, you should be good to go. Thank you.